All right, recording is rolling. It is Wednesday, May 22nd. So we're on this exam schedule. You just have periods 6 and 5 today. Tomorrow it's 4 and 3. The day after is 2 and 1. So that'll take us to the end of the school year. Remember to turn your laptop to one of your teachers at some point. You can turn it to me later today if you like. All right, so I'm going to keep going over these solutions. We're going to finish. Oh, pause this. All right, recording resumes. Back here. All right, so we were most of the way through this one. So quick recap. There was this uniform bar. There was a string. Right? There was this hinge point that it could pivot about, except the string was holding in place. They're looking for a free body diagram, so we looked at that yesterday. Right? Weight of the bar, tension of the string, and there was also a force from the hinge point that had both horizontal and vertical components. So we got that. They're saying, hey, what if you change the angle of the string? What would happen to the tension? Right, so with the shallower angle from the horizontal, the tension would go up. Right? And they said, derive an expression for the magnitude of the tension. Okay, so now we're going to hit the math. Okay? So we did that. We went through torque and came up with this expression. So the tension in this string ends up being the weight of this uniform bar divided by 2 times the sine of this angle from the horizontal. Boom, that's it. Now we get this expression. All right, so that's about where the bell was ringing yesterday. Right, the question after part D. Is your equation derived in part C consistent with your justification in part B? Explain your reasoning. So I'm going to write a little bit bigger, which is a little smaller. We got the tension force is equal to, I'm just copy pasting the answer from the end of class yesterday. The weight of that bar divided by 2 times sine of the angle from the horizontal. Okay. So we're comparing part B and part C. And we're saying, is it consistent? Right? AP likes to ask this question pretty much all the time. The ideal answer is yes, and it is in this case also, right? But now we got to justify why. Right, so we're saying if this angle is smaller, so we go from this large angle to small angle, so we're making the angle smaller, the tension should increase. That's the claim we're making back in part B. That's the box we check. Right, now we've got an expression that could answer that question. Let's take a look at that. Right, so what's the relationship between this angle and this force? Right, well, if this angle could go up to 90 degrees and we're taking it closer to 0 degrees, guys, if you take sine of smaller and smaller numbers, say if you start at 90 degrees and go to 80, 70, 60, 50, 40, right, you're getting smaller and smaller. What's happened to the sine of that angle? Is that also getting smaller? Yeah, right? Right, now, how about the overall fraction? Okay, so the weight is the same, 2 is a constant. So we got a fraction where the denominator is getting smaller, 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 which makes the overall fraction what? Bigger, right? Because you divide by smaller values, you get bigger overall fraction. Hey, and that would correspond to a larger tension. Yeah, so I would write that out in sentence form, right? Of course, I'm just doing that verbally, but that would be the answer. Okay, guys got it? All right, the string is cut. The beam begins to rotate about the hinge with negligible friction on the following axis. Angular speed is a function of time. Sketch the angular speed of the beam as a function of time while the beam falls, but before the beam becomes vertical. Ooh, now this one's a little tricky, a little bit critical thinking, right? Because, there's this dynamic scenario. Right. So here's what I'm going to use to guide my thinking is I know that torque is equal to I times alpha, right? And relative to this hinge point, this, they call this a bar or beam. Calling it a, let me go try and keep using beam. Okay. So this beam has a constant rotational inertia about that hinge point, right? So that's not changing, right? Now, interestingly, the torque is changing. Here's why. Even though the weight of the beam is constant, this angle is changing. Or whoops, sorry, actually, scratch that. I shouldn't be pointing at that for a minute. I should be thinking about it like this. Guys, torque is R cross F, right? Now, if you cut the string, so the string's gone. The string's out of the picture now. This beam's gonna rotate down this way, right? And there's a torque causing that. So the weight of the beam pulling at L over 2 initially. But guys, what happens to that L over 2 as this is rotating? It's getting what? It's getting smaller, right? Which means that the torque is also getting smaller. Right? Now, this graph has none of these variables on it, but I'm using it to guide my thinking. So why, right? Because, guys, what property of the graph that I haven't drawn yet, but you guys drew on your FRQ, guys, what property of this graph tells you angular acceleration?
The slope.
The slope. Yeah, the slope, right? So I'm looking at actually this variable right here. I'm going to say alpha is the torque divided by I. Again, I is constant. Rotational inertia is constant. But the torque would be getting smaller because the radial arm is getting smaller. Okay. So it's going to start off as maybe approximately linear, right? But not for very long, right? Right. So alpha, there's some initial angular acceleration, but the torque is getting smaller, smaller, smaller. In fact, if I take it all the way to the part where the beam is vertical, right, where it falls down all the way vertical, at that point, the torque would be equal to what? Zero. Yeah, zero, right? And if there's zero torque, there'd be zero angular acceleration, and this actually would go horizontal, right? So now they say don't go all the way exactly to that point, right? So maybe I could get it like kind of up to there, right? I think that right there should have been an ideal answer. Maybe like concave down, you can call it, right? Guys, how many guys got that? You guys got that? Hopefully do that. Yeah, all right, all right. You've seen some winners. So be looking for, right? So I don't know how they scored it. Could have been 1 or 2 points. And yeah, that's really looking for, right? So maybe if I had to guess, it could have been something like start at 0 and have it upward sloping and have downward concavity, right? Maybe something like that. So look for. All right, number 4. Ooh, it's a pendulum. Small sphere, some angle, pull it. Let's see what we're doing this. Simple pendulum, small sphere, hanging from a string, negligible mass. Top end of the string's fixed, point A. Makes small angle from the vertical, as shown. Sphere release, so it swings straight point B, which is the lowest point. The work done on Earth. The work done on Earth by the sphere is W subscript E. Work done by Earth. Okay. Guys, pause right there. Oh, what could that be equivalent to working off this diagram? Okay. Guys, is there a height change from point A to point B?
Yes.
Yeah, there's a really small height change. Maybe I'll call it H, right? Or delta H if you like, but maybe it's H, right? Right, do you guys know what that is relative to this angle? You guys remember it's the length of the string times 1 minus cosine of the angle? Right, you guys remember that? Let me find the, I know I have a poster to back that up too. Let me dig through these real fast. And now I'm gonna back that up. There it is. There it is. It's right here. All right. So you guys remember this one? This one? All right. So L 1 minus cosine theta. Right. It's height change. Okay. And then when they say the work done by Earth, guys, the work done by Earth due to that height change, is that also equivalent to the potential energy that it started out with, which is like mgh, right? Mm-hmm. So I'm gonna write that note. I'm gonna say the work done by Earth is equal to mgh, where h is this whole expression right here, because you guys remember geometry from class. Right, the pendulum is then taken to planet X. Ooh, we're switching planets. The mass of planet X is the same mass as Earth, so same mass planet, but the radius is greater than the radius of Earth. Ooh, the sphere is brought to point A, so the same angle, so same pendulum, same angle, and then it's released and swings through point B. The work done by the sphere on planet X is W sub X, right? Which should be work done on planet X is also mgh, but it's the gravity on planet X. So put a little subscript on that X right there, H. People retroactively put a little subscript E on the original one for Earth, right? mgh, right? But they're different gravity fields, right? Right? Justify why the work done on planet X is less than the work done on Earth. Oh, look at that. So AP is being nice again, because they could have asked you, would it be more or less work or the same, and had you check a box first, right? But they're telling you it's got to be less, and they just want to say why, right? So I would probably jot these 2 expressions down. And also, guys, who remembers gravity field of a planet is equal to what? Starting from universal gravity constant times what? Mass of the planet divided by
radius squared.
Radius squared. Yeah, g on r squared, right? I would jot that down. I think look for some kind of paragraph type answer, but if you have that expression written and you refer to that, right, that would definitely stand out to an AP grader, right? Right. So here, what's going on here? So same mass as Earth, right? But a larger radial size. Guys, if there's a larger radial size, then what's the gravity field on planet X compared to Earth? More or less? Less, right? Like if it's twice the radial size, it'd be 1/4 of the gravity field, right? But the important thing, it's less. So you write that somewhere out in sentence form, right? And now I'm going to bring in these expressions for comparison. So work is mgh. It's the same mass bob. It's the same height change because the same geometry of the pendulum, right? But with a smaller gravity field, that would effectively also be less work. And so I would mention all those details, right? I point to this, point to these, and then say smaller gravity field means less work done. Okay, all right, guys, good. Okay, number 4 continued. A new pendulum made by hanging the same small sphere from a different string, also negligible mass on the string. The new string is slightly elastic. That's interesting. Slightly elastic string. We hardly ever deal with that in this class. So imagine, how about a rubber band, right? You guys think as it's swinging, it's not going to be a constant length anymore. It's going to be like wow, wow, wow. It's going to change length as it's swinging. And the length of the string may increase or decrease depending on the tension applied to the string. Okay, when here, and let me kind of draw that out. Here's what I'm thinking. Okay. So if it was a constant length string, it'd look something like this, like a constant radius, going back and forth, right? But if it's elastic, maybe I'll exaggerate this a little bit. Do you guys think that could be something like this, like maybe something more like that? You guys think? Okay. So I'm thinking about that. New pendulum taken to a different planet. Oh, whoa, did I miss something? On Earth, the spheres again display single theta, released from rest. And it takes some time period to oscillate TF. Okay. Okay. No, well, I know for a constant length string, time period is 2 pi times square root L over G, where L would be a constant value. Now for this rubber band elastic type string, that L is not going to be constant anymore, right? In fact, if anything, it'll probably be longer, right? Overall, like on average, right? Speaking of which, here, this elastic string compared to the regular length string, right? Guys, if this L can possibly get a little bit longer, that makes the time period overall what? Also larger, right? You guys see that? Larger time period, okay, just comparatively. Okay. Okay, and then we're going to throw in another variable. The new pendulum is taken to a different planet, planet Y. The radius on planet Y is the same radius on Earth, but the mass has a larger mass than on Earth. All right, so I'm going to break out this one again. Gravity field is gm on r squared. Now they said the same radius, but a larger mass. All right, guys, if you have a larger mass, all else equal, that's going to do what to the gravity field? Also larger, right? So, okay, so we have a larger gravity field. On planet Y, when the sphere is again displaced from the vertical and released from rest, the new pendulum oscillates with time period ty. Right, but yeah, it's kind of look like this one, time period. Well, you'll say y equals 2 pi times square root. I'll say L long. How about that little subscript? Because on average, it's going to be longer if it's got this elastic property. Right, you guys got that? All right, okay. And I'll throw a little subscript y on the g, right? G sub 1, right? You guys see that we've effectively got two type variables, two independent variables, I should say, right? Which we normally try to avoid in class, right? One of the variables we've got is instead of the steady length string, the constant length string, now we've got this elastic string that's changing. The other variable we've got is we're also increasing the gravity field at the same time, right? Ooh, guys, look at this competing effect. Longer length and a larger gravity field. Do you guys see those two competing effects? Well, yeah. They could possibly cancel out, or if one's more dominant, then it could drive what's going to happen to time period Y. So what happens to time period Y? At this point, it's ambiguous. You guys see that? All right, what are they asking here? In a clear, coherent paragraph length response that may contain drawings. Ooh, okay, so these drawings would probably be helpful. Maybe if you threw down these formulas like I did, these expressions, that could be helpful. Explain how time period Y. Oh, look at here. Could be larger or could be smaller than the time period on Earth. Okay, well, okay, actually, just stepping through the thought process, I kind of already explained that, right? So we got, I would explain that. I would write down everything I got so far. I would write down, right? Then I would say, right, this length is longer, but this gravity field is also larger than on Earth, right? So you got this competing effect, right? And yeah, and either of those variables could dominate, right? Depending on exactly Yeah, exactly how much and whatnot. Right. So something like that. All right. Some version of that. Okay, you guys good with that? Yeah. All right, there you go. Could say a little bit more about that, but that's probably all they're looking for. Right. Ooh, guys, from that diagram, I'm already thinking this looks like probably a collision and maybe something to do with conservation momentum, I'm guessing it looks like. All right, let's check this out. Figure 1. Oh, they threw a little time on here, times 0. 6 kilograms, 2 kilograms. Okay. Time 0, block A slides on horizontal surface toward block B, initially at rest. Shown in figure 1, the masses are 6 kilogram, 2 kilogram, respectively. Oh, the blocks collide elastically. Ooh, elastically, which means, here, let me dig up my poster for elastic. I got it right here, ready to go, ready to go. Right, elastic collision. Right, so I'm already thinking about these two properties. Now, the top property, conservation of momentum, that could actually be for any kind of collision. But when they say elastic, I know that also opens up the second condition, that kinetic energy is conserved. Right, so I'm thinking both of these green box fights. Right. As a, okay, and that's after 1 second. So 1 second after the figure. Collision, elastic collision. As a result, the magnitude of the change in kinetic energy of block B is 9 joules. All frictional forces are negligible. Determine the speed of block B immediately after the collision. Wait, you must have asked something else. Okay, yeah, okay. So let's do that first. Right. Actually, this one, I think just the fact they gave you the energy, that's really all you need to get the energy and the mass. That's all you need. Right. Guys, kinetic energy. Did you guys write kinetic energy is 1/2 mv squared? And I think we can get everything from that because they want speed of block B. They told us the energy is 9 joules. 9 joules will start from rest. The change is 9 joules. Therefore, the final energy is 9 joules. 1/2 mass of block B is 2 kilograms. And we're solving for B. That's it. Some algebra. Oh, but look at this. 1/2 and 2 cancel. Guys, this is something you guys have seen over and over and over again in many practice problems that I've assigned you guys, is that 2 kilogram block is really common block, especially when they ask energy questions for this very reason. The 1/2 and the 2 cancel out. So make sure calculation's easier. Square root of 9 is 3. So V should be 3 meters per second. Right? Right. So that should be right. You guys hopefully get that. Okay. All right. You know what? While we're at it, I'm going to go ahead and say what happened to block A. And we have 2 ways we could get it. I could do this way or this way, and I should get the same answer either way. Right. So I just pick my favorite. Here, let's do conservation momentum. How about that? Right. So they didn't ask this, or at least not at this point. Maybe it's the next question. I don't know. I forget. Okay. But let's do conservation momentum, and because I'm just curious to see what happened to block A. I got 6 kilograms. Was initially moving at, oh wait, did they not? Never mind. They didn't actually tell us. Okay, okay, never mind. I don't think I can solve that. Never mind. Right. Because we don't know the initial. There's too many unknowns. Let's check this out. Right. Okay. Except if I had this graph, I could have answered that actually. Right. Because they give us a position versus time graph, and look at this. It's leading up to the point of the collision. Right. So from this, you could get the speed of block, velocity of block A, just be the slope of that line. Okay, so you got that. Right. Oh, and they also gave us the center mass line. Now, if you go back to look at the relative masses of these blocks, 6 kilograms versus 2 kilograms. You guys see it's a 3-to-1 ratio, right? You guys see that? So another way to think of it is that the small block is 1/4 of the total mass, and the large block is 3/4 of the total mass. You guys see that too? Right? Now, you could run the center mass equation on this, right? But it's just a weighted average. And that's exactly what this dashed center mass line shows. You guys see it's 3/4 of the way weighted towards the larger block, block A, and then only 1/4 of the way towards the smaller block, block B, right? And that's always true regardless of what time you're looking at, okay? And then, of course, when they collide, then the center mass is at that point too. That graph shows the positions of block A and B and the center mass of the 2-block system from 0 to 1 seconds, right? So up to the collision point. On the graph, draw and label the lines to represent the positions of block A, B, and the center mass between 1 and 2 seconds. So the rest of the graph, basically, right? Each line should be distinctly labeled. So now they were helping us out here by telling us this kinetic energy transfer, right? So let's play off this. Let's assume that there's numbers are all self-consistent, which they should be. Maybe we'll go back and solve and make sure, right? But 3 meters per second is block B, block B, right? So block B was at rest, and then bam, gets hit at the 1 second point, and then takes off at 3 meters per second. So let's say that's another 1 second. It should have moved 3 meters. That's bam, bam, bam. That's here, right? So I'll draw this and I'll say this is block B. Okay, right, block B, because that line would be 3 meters per second. 3 meters per second. Okay. Now, block A, actually, here's where I actually do want to go back and solve what was the post-collision velocity of block A, and we can solve this at this point. So let's go 6 kilograms at, and we see it right here. Guys, what was the initial velocity of block A? No, block A.
Oh,
2 meters in 1 second. Is that 2 meters per second? Right, 2 meters per second. So I'll put that right here. 2 meters per second, right? Now I'm doing conservation of momentum. I could go through kinetic energy because it's elastic, but just pick this one, right? And then that's the initial momentum. Is all provided by that block. And now post collision, I got the 6 kilogram block moving at some, I'll call it V sub A, that I could solve for, right? Plus the 2 kilogram block takes off at 3 meters per second, and I know that because, well, I'm assuming that the numbers they gave me are all consistent for this particular problem, right? I do want to confirm that also with kinetic energy, but I'm going to save that. So 1 step at a time here. All right, let's see. So I got 6 times 2 is 12, 2 times 3 is 6. Okay, so what's 12 minus 6? 6 divided by the 6 kilograms is 1. Yeah, and that'd be meter per second if you cut the units. 1 meter per second, right? Right, so that's not the answer to part A. Part A, the answer is just 3 meters per second, right? But I did a little extra here, right? 1 meter per second, right? So block A post collision takes off at 1 meter per second. Okay. So after another second, it's only moved 1 meter. That should be like this right here. So this right here should be block A, right? See block A slowed down a little bit and block B took off really fast, right? Notice that the change for block B is much greater than block A, right? Block A, pow, took off real fast, but block A slowed down a little bit, but hardly at all, because block A has like 3 times the inertia. Right, so it's not gonna move, right? Right, now before I keep moving on, I do want to confirm these numbers with kinetic energy. Let me do a kinetic energy check. So is the sum of kinetic energy initial equal to the sum of kinetic energy final, right? Put a little question mark here. So let's check this out. So let's do 1/2 mv squared. So 1/2 times the initial block move is 6 kilograms times 2 meters per second being squared. That's 12 joules initial, right? Now, is this equal to 12 joules final? Let's see. So there'd be 1/2 times 6 kilograms moving at 1 meter per second being squared, plus 1/2 times the other guy was 2 kilograms. And we said it was moving at 3 meters per second. Square that, right? All right. So I haven't tried this out yet, but when I hit enter, the answer is better be 12. If it's not 12, there's something messed up. Oh, good. It is 12. Woo! 12 joules. All right, check. Aha. All right. So all the information AP gave us is completely self-consistent, which is good. Good deal. Right, so 12 joules, 12 joules, right? So now, check both of these. I'm getting consistent answers on both of these, which confirms the elastic, so we're all good, right? Now, one more thing. I was supposed to do 3 lines, right? So let's do the center mass line. Guys, what have I been telling you happens to the center mass after a collision? Keep doing what it's doing? Yep. There you go. Just keep on chugging. What should be just like this. Tick, 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 tick. Just keep going straight line. Oh, and look at that. Look at that. You guys remember how before the collision, you take a weighted average. It looked like this center mass line was like 3/4 of the way over towards block A. Okay? And after the collision, that's also true because the blocks have the same mass after as before. So the weighted average is still true. So maybe it's another approach you could take to get that too, right? So we got equations, conservation momentum, kinetic energy. We got graphs, right? And it is all lining up. It's all telling us the same story, and everything's completely self-consistent. Yeah, so this is all good. Okay. Part C. Consider if in the original scenario, instead of colliding elastically, the blocks had collided and stuck together. Well, that'd be like perfectly inelastic. Describe how the line drawn for the center of mass would change, if at all. Briefly justify your response. All right, so we're just focused on this dashed line. So I'll say this is a center of mass, of course, it's dash. Okay. Okay. Guys, would that dashed line change what it's doing? No, it'd be the exact same. So I'd say it's the same as before, same as elastic. Right? And I would say something like no external forces. Maybe no net external forces, because there's weight and normal forces, but those just cancel out. You could effectively treat this as a closed system. I bet if you wrote closed system, they probably gave credit for that. If you said the forces are only internal, okay, so something like that. Okay, so it's the same, and here's my justification. Boom, boom. Okay. All right, guys good? Okay. Oh, that's it. That's the entire packet. All right, we are done.